Last episode, one qubit was two amplitudes, and we drew it as two bars, one for the 0 outcome and one for the 1 outcome. One qubit is not where the interesting things live, though, so let us add a second qubit and see what the picture becomes. Here is the surprise. Two qubits are not two amplitudes plus two more. The state space of two qubits is the tensor product of the two single qubit spaces, and a tensor product multiplies dimensions rather than adding them. 2 times 2 is 4, so two qubits are described by 4 amplitudes. One for each 2-bit pattern, 0, 0, 0, 1, 1, 0, and 1, 1. Those 4 patterns are the computational basis, and now our row of bars has 4 bars instead of 2.
Wait, why 4? I would have guessed 2 plus 2. Where does the multiplying come from?
Because each basis state of the pair is a joint choice, a value for the first qubit together with a value for the second. 2 choices for the first times 2 for the second gives 4 combinations. Add a third qubit, and it is 2 times 2 times 2, which is 8. Every qubit you add doubles the count of amplitudes. Hold on to that doubling. It runs through this whole episode in 2 directions. It is where entanglement will hide, and it is the wall that makes these machines so hard to simulate. A fresh 2-qubit register starts in the 00 state. The first bar carries all the amplitude, and the other 3 are flat. In code, it is exactly what you would hope. Make a 2-qubit state vector, and its amplitudes are a length 4 array, indexed by the 4-bit patterns in order. 1 qubit fit in a length 2 array, 2 qubits fit in a length 4 one. Still just a vector, only a little longer. Let us prepare the 2 qubits independently. Give each one a Hadamard, the gate from last episode that turns a definite bit into an equal superposition. 1 qubit into an even mix, the other qubit into an even mix, side by side, with no interaction between them. Watch the 4 bars come up together, all the same height, each amplitude equal to 1/2. This is a product state. Because we built the pair by preparing each qubit on its own, the joint description is just the 2 single qubit states multiplied together. And a product state leaves a fingerprint you can check. When the amplitudes come from multiplying, the amplitude of the 00 times the amplitude of the 11 equals the amplitude of 01 times the amplitude of 10. Both sides are the same product of the underlying single qubit numbers, so they must agree. For this even mixture, 1/2 times 1/2 matches 1/2 times 1/2. The check passes. The state cleanly factors into a part for each qubit.
So does every 2-qubit state split like that, 1 clean piece per qubit?
That is exactly the right question to ask, and the answer is no. A product state is the special case, the 2 qubits that happen to know nothing about each other. Most 2-qubit states fail that check. The ones that fail cannot be described qubit by qubit at all. They have no classical picture, and they are what the rest of this episode is about. Now let us make a state that does not factor. Put the first qubit into a superposition with a Hadamard, and then add 1 new gate, the controlled knot. It flips the second qubit exactly when the first qubit is a 1, and leaves it alone when the first is a 0. Watch the bars rearrange. The amplitude collects on just 2 patterns, 0, 0, and 1, 1, each at 1 over the square root of 2, and the 0, 1, and 1, 0 bars fall to nothing. This is a Bell state.
I think I already get it. It is just 2 coins that always match. Someone flips a hidden pair, they land both heads or both tails, and you only ever see them agree. That is ordinary correlation, nothing exotic.
I do not buy that. If it were 2 hidden coins, each coin would have a definite face before anyone looked. So tell me, does the first qubit have a value of its own here, sitting there waiting?
George has put his finger on it. Run the same factorization check we just used. The amplitude of the 00 times the amplitude of the 11 comes to 1/2. The amplitude of 01 times the amplitude of 10 comes to 0. 1/2 is not 0, so the check fails. And it fails for every possible pair of single qubit states. There is no state you can assign to the first qubit, and no state you can assign to the second, whose product rebuilds this vector. So the first qubit does not have a state of its own, only the pair does. That is entanglement. Not a hidden mechanism, but the absence of one. The joint vector simply refuses to come apart into a piece for each qubit. And the whole preparation reads as a tiny circuit, a Hadamard on the first qubit, then a controlled knot onto the second. 2 gates, and you have built a state with no classical shadow. Here is the consequence you can watch. Measure the first qubit of the Bell state. The bars collapse the way they did last episode onto a single outcome, say the double zero. Now measure the second qubit. It always agrees. The first measurement already fixed the second because the surviving pattern left only one option standing. Sample the unmeasured state many times and only 2 results ever appear, the double zero and the double one, each about half the time. The mismatched patterns never show up at all.
But those are exactly the counts 2 matching coins would give me. Half the time both heads, half the time both tails. So where is the real difference?
Fair challenge. In this one measurement, there is no difference. The matching coins reproduce these numbers perfectly. The difference is in what the coins quietly assume and the amplitudes deny. That each qubit carried a definite value all along, before you looked. Measure the pair along a rotated direction instead, and the hidden coin story predicts one pattern while the amplitudes predict another, and the experiment sides with the amplitudes. That is the crack the coins cannot survive, and it is why we needed a new word. And nothing spooky is being smuggled in. Nothing was hidden, and nothing travels faster than light. The correlation was written into the joint amplitudes from the moment the controlled knot ran, and every outcome we sampled was already sitting in that one vector. Measuring the first qubit is measuring the second, for the plain reason that the vector describing them never split into 2. Adding a qubit doubled our array and bought us a genuinely new thing, a state that has no parts. Now come back to that doubling, because it is the other half of the story. Every qubit you add doubles the array of amplitudes. 10 qubits is already 1,000 amplitudes, 20 qubits is 1,000,000. 30 qubits is over a billion complex numbers, all of them alive at once. The state grows fast, but 1 billion numbers is still something a computer can hold. The real trap was in how we applied gates. Every gate so far was built as a full matrix stretched across all the qubits and multiplied into the state. But such a matrix has 4 raised to the number of qubits. Entries, the square of the state itself. At around a dozen qubits, that matrix stops fitting in memory. The scaling post fixes it with one idea: never build the matrix at all. The trick is to see the state vector for what it really is. Not a flat list, but a grid with 1 axis per qubit and 2 entries along each axis. A gate touches only its own qubit's axes, so applying it is a contraction. A single tensor product that sums over just those axes and leaves every other qubit untouched. That costs on the order of 2 raised to the number of qubits, not 4 raised to it, because it never visits the qubits the gate does not act on. The whole engine is about 5 lines, and it is real code you can read.
So even with the clever engine, does a classical computer just run out of room eventually?
It does. The state itself is the ceiling now, 2 raised to the number of qubits complex amplitudes. Around 30 qubits, that is tens of gigabytes, and a few qubits past that it is a terabyte. A laptop tops out near 30, a supercomputer maybe 50. And that is the punchline of the whole episode. The exact place where the amplitudes outrun every classical machine is the same place a quantum computer might do something we cannot. The exponential wall is not only an obstacle, it is the hint about where the advantage lives. Next episode, we put these amplitudes to work, circuits and interference.